how is the... So I'm glad to see that assignment 1, 7 have submitted. Assignment 2 and 3, 4 have submitted. So to those who have submitted, keep it up. You are keeping pace with the class. For those who have not, it's starting to get a bit worrying because the last week is actually the 3rd week of July. So we've got slightly more than a month only. And the first 3 modules are actually the easiest one, the logical effort and the process variations. That's a little bit more challenging to get. So I think really you have to try to put a bit more effort to finish this up. Okay, Eugene, maybe you could start off with your questions, like anything you're unsure of, since you I guess you have some questions, right? You wanted us to review.
Yeah, Doctor. So,
Okay.
chapter 1 was actually very clear.
Okay.
But chapter 2, it's slightly cloudy, Doctor, because I'm trying to understand in what is the real extract they're asking. So I'm actually stuck in question 2.1 and then at 2.14.
2.10 and 2.14.
Yeah, 2.10 and 2.14.
Okay. So let me take a look at it and see how we can try to address that. I'll do my best not to give away the answer as usual, but try to address the fundamental aspect of it. Okay, let me just go ahead and share my screen. Okay. Okay, so we go to question 2.1 volts. Okay, so I'll just read the question, Eugene. An NMOS transistor has a threshold voltage of 0.4, so VTH, and a supply voltage of VDD 1.2. So what the circuit designer is trying to do is trying to say, let me try to replace this transistor with one that has a VTH of 0.1 volts, okay? So it's just asking you how much more would the saturation current increase for an ideal transistor. Okay, Eugene, this is the one you're looking at, right? Or you're looking at 2.1?
2.10, sir. Yeah, you are right.
2.10. Okay. So here the most basic part of things, guys and gals. Okay, let me just open my PowerPoint. I need you to understand the current voltage relationship of a MOSFET transistor, most basic element. Why? Because that helps you to reason about the transistor and its speed to a first degree. I mean, it's not going to be perfect and all that, but it does a pretty good job of it. So you want to actually know the drain current. It goes, let's insert the equation. I guess mu is the mobility. Mu C ox, oxide thickness, W over L, and then this is VDD minus VTH squared. So this is the ideal, I think this is VGS minus VGH. Okay, this is the ideal saturation current. Then there's another one that's actually like this, VGS minus VTS, and then times by VDS, right? Right. So what this actually says, okay, if I draw my MOSFET, okay, you have to understand. Okay, I just draw you a two-dimensional version of it, okay, if you don't mind, I'm going to be a bit lazy tonight, and I'll represent my MOSFET with a funny shape like this, because I'm just a bit lazy to draw it properly. Okay, this is my, I have a well here, I have another well here, And you understand that the well is doped, right? It's just a region of semiconductor that is doped. Okay. So let's say this is it's a MOSFET, and NMOS. So NMOS, let's say this is N plus. Because it's upside down, that's why the text is upside down, N plus. And then this is my gate, my drain, my source. And what actually happens is usually we will actually connect one of these to ground, right? This one we connect it to ground. Okay, and you're looking at the voltage across, let's use a different color pen now. You're looking at the voltage across here. Why? Because when you apply some kind of voltage here, when you apply some kind of voltage here, okay, when you apply voltage here, of course, this voltage is respect to this ground here. What you're doing is you are creating a conductive channel, right? You're creating a conductive channel like that. And this one, I'm going to color it orange because this is all the electrons. Okay, yes, electrons, correct. Because this is p-type, this region here is p-type, this is n-type, this is n-type. N-type means the excess electrons flowing around, n-type means the excess electrons flowing around. So the natural carrier here, the free carrier here will be electrons. So the only problem is in the MOSFET is usually without any kind of voltage here, there's no bridge, right? There's no way for them to connect. But when you apply a voltage here on the gate, what you're doing is basically electrostatically, you're drawing all the electrons down here, you're drawing it up here to the surface. Okay, so essentially the MOSFET is actually forming a bridge. Okay, a bridge so that there's free electrons here, even though electrons are the minority carrier here. Understand, they're holes here, but they're the minority carrier here, but they get drawn up here electrostatically because you're applying a voltage here, VGS. Okay, so when you apply voltage here, there's electrons here, there is now a conductive path here, so electrons can flow. That's why you need a VGS above VTH. Above VTH is the minimum voltage to actually create a conducting channel here. That's why it's called this is the principle of MOSFET operation. Okay, so here what we're trying to say is the amount of current, the quantity of current, right, that can flow in this MOSFET. Okay, it's really dependent on how much VGS you put here. Okay, so if you put VD is actually dependent on VGS minus VTH. This is actually called the overdrive voltage because you need to exceed VTH at this point, then you form a channel. Then anything more than that, you're actually adding more electrons here. So you got more electrons, means you got a greater chance to actually source a larger current, right? Because the current is basically rate of change of electrons per unit time, right? Correct, Eugene?
Yep.
Do you follow this explanation of how a MOSFET works?
Yes, Doctor.
Okay, so again, we have various tools at our hand here, right? So the way I can talk about current is basically rate of change of charge, okay, per unit time. So dq dt. So there are two ways I can actually increase my current. Okay, I can increase my current by adding more charge so that there are more change, or I can move the charge in a shorter duration of time. You understand? Okay, there are two ways, right? So if I actually am more, if I'm actually moving the charge, like I'm moving 5 charge in 1 second, okay, so it's 5 coulombs per second. That's current, that's amperes, right? So if I want to actually double the current, I can actually move 10 coulombs per second. So that's double the number of charges in the same amount of time. Okay, so if I actually increase the gate voltage here, I'm actually adding more charges here that can move. Okay, a second way to increase current is instead of moving the 5 coulombs in 1 second, I move the 5 coulombs in 0.5 seconds faster. Okay, can you follow that?
Yeah.
Okay, so again here, we need to understand this relationship, because this relationship tells us all the levers we have to actually increase the current in the MOSFET lah. So ideally, ultimately, the current will actually be dependent also on VDS lah. That is the voltage here to here lah. But in saturation, in saturation, what actually happens is there's something called pinch off lah. Wait, let me draw that now. When you start applying a voltage here, you actually get a charge profile, something like this. When you start applying a positive voltage here, lah. Okay. VDS. Okay. So if you start applying, let's say, let's just call it VD lah. Okay, here you get a charge profile like that. If you don't have VD, you just have a channel like this. If I just apply voltage here, I just have a channel like that, right? But there's no current flowing, because in order for current to flow here, you need the voltage from the drain to the source, nah? Correct? But if this voltage starts to go up, it will become closer and closer to VG, right? At some point, the voltage here and the voltage here will be sort of the same. And that's why there's not going to be so much charge formed at this area, because the voltage here and the voltage here are about the same. So at this part here, not much channel is formed. So when you actually start applying a VD here, there's going to be a little bit of a pinch off here. Okay. And when you have a pinch off here, if you change VD a little bit more, it's not going to really change the speed of the current so much. Okay. Okay, let me now try to explain to you the kind of levers we have to pull. The first lever, of course, is we said VGS minus VTH. That is, I'm forming the channel here by electrons. So if I have more VGS here, if it's greater than VTH by a larger amount, I have more free carriers here. Okay. Then of course you remember that this is actually a two-dimensional diagram, but actually your gate is very long. Your gate is actually going to be stretching out like that. Insert. Can you see in 3 dimensions, it actually looks like this. Okay. So if you look from the top, if you're actually looking from the top here, so those people who really have the experience, you can correct me if I'm wrong. If you look from the top, this is your well. This is your well. And then you literally have, okay, let me color this gate a bit different color, so at least we can visualize it. Let me color it green, for instance. It's not that it's green, just so you can visualize. If you look from the top, it actually looks like this. Okay, this transistor, if I look from the top here, it actually looks like this. Okay, where this dimension is the length and this dimension is the width. Can you see that, Eugene? Length, width. Can you follow if I'm looking from the top here?
Yes, okay.
Can, huh? So in actual fact, what it tends to look like more is it actually looks like this. Why? Because this, when you talk about the defined 350 nanometer technology, this is the feature size they talk about. This is 350 nanometer. If you talk about 7 nanometer technology, this is 7 nanometer. Typically, of course, in modern technology, is not exactly 7 nanometer. It's a bit longer because they got a lot of extra other things here. But for a very, very crude, the technology, let's say you're talking about a 1 micron fab technology, this just means that the length here, L here, is 1 micron. Okay, that's what it means. And L is fixed. L, they actually don't change L. L is fixed. This is fixed. Okay, all your transistors will have a fixed L. What would change is you can change the width, W. So if you want to get more current, okay, you want to get more current, one is of course you put more voltage. Two is of course if you can increase the area of the gate here, right? Because this channel is not just a line like that, it is everything underneath this gate, right? So literally you're talking about the channel is actually formed like this underneath the gate. You got me? You got me? The electrons are all forming underneath the gate like that when you put the gate on top. Do you follow me, Eugene?
Yeah.
Okay, so if I want to create more electrons here, one way to do it is, of course, I can put more voltage here. Then there's more going to be attracted up. The second way I can do it is actually I can increase the area, correct? I increase the, if I double the area, I've doubled the electrons. I quadruple the area, I've quadrupled the electrons at the same voltage, because it's still the same voltage, but the voltage is applied over double the area, 4 times the area. Do you follow me?
Yes, okay.
Okay, so this is the second way we can increase the number of electrons. First is by increasing the voltage. The second is by changing the width here, this W parameter. Okay. And then the third actually is by changing the mobility, the mobility of this. What do I mean by mobility? Mobility is actually an intrinsic material property. It is actually it's a measure of how fast the electrons can move in the material itself. Okay, so usually for N-type semiconductor, the electrons are roughly 2 times faster than P-type holes. So if you got a PMOS, normally the PMOS will be double the width of the NMOS to make the current equal. Why? Because the PMOS mobility is usually roughly about half the NMOS mobility. That means the holes, the free carriers in the PMOS is roughly half slower. It's actually slower by 2 times, more or less than the NMOS. Okay, so another way is I can actually change the carriers here. Instead of using electrons, I can use holes, but of course holes is not great And another way you can think about it is in gallium arsenide rather than in silicon. Gallium arsenide, the mobility of the holes and the electrons are actually faster in gallium arsenide than they are in silicon. Okay. And the fourth way, of course, is I reduce the capacitance, right? Because capacitance is actually a function of area over distance, right? So again, if I increase the width, I'm of course increasing the area. But I can, if I reduce the distance, for instance, if I reduce the distance like that, I can have more current because reducing this distance will increase the capacitance, right? Because you remember your capacitance is basically nothing else but Cox is epsilon epsilon A over D Okay, A is the area here, D is the distance here. So I reduce the distance, or I can increase epsilon, that is I change the dielectric constant of the layer in between. So the reason I need you to understand this equation is because I need you to understand all the tools and tricks we use to actually increase the current. Do you get that?
Yeah, okay.
Right? Because why we want to increase the current? Because the more current you have, the faster you can drive your circuit. Of course, you burn more power, but current is rate of change of transfer of charge, right? Right? So if I got a fixed capacitance, a fixed wire being charged by more current, it will charge faster, correct?
Yep.
And if I have a capacitance with a certain amount of charge and I discharge it at a higher current, it will discharge faster, right? So current is your golden thing here. Current is basically a proxy for speed. The more current you can pull out of this, the more speed you can get. Okay. All right. So this is actually the equation now. Now I'm just talking about this, but this is the saturation. But actually, before you reach saturation, you actually have this equation, which is actually the amount of current is dependent on the VGS here, as well as the VDS here. VDS here is actually the driving force. How fast am I pulling the electrons from here to here across this channel? Okay. So of course, if I have a higher VDS, I'm going to pull it faster, right? Do you agree with me?
Yes.
All right. Okay. So you should also understand okay, here I'm going to be telling you things from microelectronics and semiconductor physics You may not have that background, but it's okay there are two main driving force for current. Okay. One is called drift current, and one is called diffusion current. Okay. Drift current, basically the idea is going to be proportional to an electric field and the mobility so it's going to be proportional to mu times the electric field. Okay. So when you see electric field, you're like, voltage, because electric field is actually voltage per unit length, right? Okay. So when you have VDS here, you are actually your current is actually a drift current, right? You're using the voltage across here to actually attract electrons, right? So you can actually argue that the amount of current I can pull depends on my attractive force. How many electrons can I pull up into make this channel to participate, and that's dependent on the voltage here as well as the area over which I'm applying that voltage, right? Because this layer of channel is actually three-dimensional There's a certain depth here, and there is a certain area on the top here right? So if I have a larger width transistor, I can pull up more current, and there's more current for me to pull okay. And of course, by the material properties, the oxide thickness as well as the mobility. Okay, so if I keep pulling VDS, 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 at some point, the way you can think about this is that you remember the channel is actually formed because the voltage here, there is a voltage at this node to this node, right? Voltage to this node to the node. So this is 0, this is VGS. So VGS to here, there is a voltage VGS there is a voltage here. But if this voltage here start to become close to this voltage, there is a smaller and smaller up to some point, there's actually no voltage difference between these two nodes, right? Do you see that?
Yes,
So I start increasing this because I want to keep pulling more and more. But as I increase this, I'm reducing the voltage difference between these two, which means very close to this part here, there's not that much attractive force to pull out electrons, correct?
yeah.
But there's still a great electric force here because this is Vg and this is 0. This is 0 volts. So there's still a large force to pull out the electrons. So I have sort of like an imbalanced channel when Vd becomes very large. I have sort of like an imbalanced channel because near here, this voltage is either the same as this or this voltage is actually larger than this. So there's going to be a region here very close where there's almost no voltage difference. It's of course not going to be larger than VTH, means that I'm not actually having electrons here. Okay, Ken? So this is where this equation comes. This equation comes in the case when VDS is very large, that means much larger than VG, so that the actual current through here is no longer going to be dependent on VDS because this VDS is already so high up to the point that actually in physical terms, this channel is already been cut off already. There's a pinch off here. There's actually a small gap here. There's no free electrons. Okay. So what actually happens is that because of VDS, there is an acceleration, there's a driving force, the electrons are accelerating. At this point, even though there is no continuous channel, they just kind of have so much momentum, they just jump over. Okay, that's what's happening. And so when this pinch off happens, even if you increase VDS, you are not going to actually increase the current by much. You're not. Okay, that's why there's no longer any VDS dependence here. But you can actually increase the current in a squared way by Vg. Like any increase in Vg will actually increase it by squared. This one, there is a derivation in textbook, but at this point, you need to understand these are the basic equations describing how to increase the current in your MOSFET. Do you understand that?
Yeah.
Okay, then we can go to 210. 210 is asking you, okay, so this is already saturation, right? Because the current does not change with VDS, right? So I'm looking at this device now. Let's say I suddenly change, I do some kind of engineering to this material. Engineering this material is going to change the threshold voltage. So I'm changing the threshold voltage from 0.4 to 0.1, meaning that somehow I'm making it easier to form a conductive channel here. Then I'm asking you the simple question. If I do that, how much more current can I get for the same transistor where I change the threshold voltage by engineering the material to 0.1 volt compared to the original transistor at 0.4 volt? You think you can answer that?
You can.
You can, right? You sort of see the picture already, right? Okay, very good. Okay. All right. I'll go to sub-threshold leakage a little bit later. Okay, so I just want to finish up on this one here, since we're talking about this one. Now, this is what we call the long channel equation. Why? Because it's an ideal MOSFET. It tends to hold for 1 micron feature size. Lambda equals 1 micron and above. That means very, very old technology. Nowadays, today you have 7 nanometer, at least 1,000 times, almost 1,000 times smaller in size. What actually happens as you shrink this, you are getting into a regime that is something like this. Okay. And physically, you are actually having a very, very short. You're talking about because you're shrinking your gate size like that. This is what the modern transistor looks like. And this is why it's called a short channel, because the channel is literally very short. It's 7 nanometers nowadays. Okay, and you can count one atom is on the order of angstrom. That means roughly about 10 nanometers. So you are roughly the size of 2 or 3 of atoms. That's the size of your channel. Okay. But what has not changed is the voltage across here is still the same, more or less. It's about 1.1, 0.9, around there. Okay. So the voltage hasn't changed, but the length has changed by 1 order magnitude, 2 order magnitude. Okay, voltage didn't change, length changed, which means that electric field has gone up by 1 order magnitude, 2 order magnitude, by 10 times, by 100 times more. So under the situation of very high electric field, there's something interesting that happens. Okay, the velocity of the electrons here, if you start applying a VDS, on this channel here. Okay, now I start applying a small VD here. Okay, and then I get a small VD here. I start getting current going, right? The drift current. Then I increase the VD a bit more. I get more and more current. Before I even hit pinch off, at some point, the velocity of the electrons are going to saturate. It's going to become fixed. Why? Because there are certain effects on high field. Number one, you actually get more scattering. The electrons will start whacking each other more into the lattice, so they get slowed down. Okay, and number two, there's a mobility effect as well. Okay, so there's an effect called velocity saturation, which is sort of like saying that this transistor is a little bit weaker because in the long channel case, the velocity of the electrons. So drift current, the current is actually coming from the electrons are traveling faster. That means you're moving not more electrons, you're moving electrons faster. So if you double the electric field, you're moving electrons twice as fast. If you quadruple the electric field, you're quadrupling the electrons very fast, as 4 times as fast. So you're getting more current because you're moving the electrons faster, not adding more electrons. This is under drift current. But when you have a short channel, the velocity of the electrons is no longer linear with the increase in VD. At some early value of VD, there's some early value of electric field, even before the pinch-off occurs, the electron speed saturates. And so what happens is, this is no longer something to the power of 2, it's something to the power of 1 point something something. Okay, so your current is a bit weakened here already. Okay, and there are certain other extra effects, but the key one is actually your current is actually weaker. It no longer actually follows the square law rule. It's actually less. Okay, that is for what happens in short channel effects. We are going to be, this is part of the things they're asking you to study. That is, you have to understand what happens in modern transistors when the channel become very short and all of these things these ideal equations no longer come into play lah. Okay, you can follow that.
Yeah, kind of.
Yeah, that one I explained in the videos. It's got more detailed explanation in the videos, but this is just giving you the big picture, so you can go back and listen to the videos and you can everything piece together. Okay, all right. So it's very good. This is the first relationship you need to understand: the current versus voltage relationship, and what are all the levers you have in your MOSFET in order to increase the current. First thing you need to understand. Okay, the second thing you need to understand in module 3 is the capacitance and voltage relationship. Why? Because you will see that these capacitance here it says Cox W over L. That is the capacitance here, right? Because Cox is the epsilon lah. Okay, and W over L, you find that WL, that's the width, the area here, and then that's the distance here. That capacitance, depending on whether what voltage you apply here at this point here, you will actually get different capacitance here. And if you look at it, there is also a stray, something called a fringe capacitance between this one and this one. Because again, this is just a few nanometers thick, right? So it's very, very, and this oxide also is also a few nanometers thick. So this is a conductive layer. There's free electrons here. Even though it's not metal, there are free electrons here. This is a conductive layer, right? This green gate, right? It's conductive layer. Long time ago, it used to be metal. Now this is a silicide. It's a form of a silicon, type of silicon. This also got free electrons here. So whenever I have two conductors with free electrons, that is the definition of capacitance, right? So I actually have a capacitance from this node to this node. This is called the depletion, the junction capacitance, the parasitic capacitance. I also have a capacitance from this node to this node. Okay. And then you stare a bit more, and you realize that, yeah, this is a p-type, and this is an n+. And when I have p and n, what does that look like to you? I have a p and an n, and I have a junction. What does it look like to you? No, when I have a p and an n, it's a diode, correct? P-type and n-type, you get a diode. Right? Your basic physics. When I have a n-type region and a p-type region, I have a diode, right? This is a diode. You remember this? Yes. It's coming back. When I have a p-type, I have an n-type. So what happens when you have a p-type region and an n-type region? N-type has a lot of free electrons, p-type has a lot of free holes. Then you join them together, you touch them. Okay, I mean, this is conceptually when they actually built by just changing the doping. So what happens is the free electrons, suddenly see here got a lot of holes here. So the electrons will start flowing over the other side. And then the holes will start flowing over this side. And then they recombine, right? So here there's no net charge, but because the electrons escape here, there's a positive charge here because there's a lack of electrons here. What happened to the lack of electrons? The electrons went over here, combined with the holes. So there's a lack of holes here, there's a lack of electrons here. So there's a region at the junction here where there is very little free charges. Here in the n-type, a lot of electrons. Because you dope it, you put a lot of electrons. Here in the p-type, a lot of holes. You dope it, you put a lot of holes. But when you touch them together, the holes will jump over, the electrons will jump over, they will recombine so that this region around the junction is the reverse bias. There's a natural reverse bias here, right? That's why diode not conducting. That's why you have to have a voltage, because that voltage is actually trying to undo the natural tendency for the holes to go here, to the electrons to go here. So when you reach, let's say 0.7 volt for silicon diode, right? It means that this region here has its negative charge restored. This region here has positive charge restored. If you remove, let's say you remove, there's no 0.7 volts here for silicon, then this region actually, there is a reverse bias 0.7 volts here. Why? Because all the electrons go here, all the holes go here, and then this region actually has no free carriers or very little. So what happens when you have a conducting layer and a conducting layer and a layer without conductance? There is a capacitance across the diode. Okay, and when you have a capacitance across the diode, everywhere along here, in the source, the drain, the source here, everywhere around here, there is a capacitance to the bulk, the p-type bulk. And everywhere along here, there is a capacitance from the drain to the p-type bulk. So there are two sources of capacitance at the source and at the drain. One is the gate to source, the gate to drain capacitance. One is the drain to the drain to bulk, source to bulk capacitance. And this is called a depletion capacitance because it's a capacitance arising from a depletion layer because of the N and the P type here. There's an implicit diode form here. You got that? So what we're going to do is we're actually going to see that when you draw your MOSFET, let's go for MOSFET. Tonight I'm a bit lazy to draw the MOSFET. So I just point a bit can. If you don't understand, you let me know. If you draw your MOSFET like this here, this is the source, this is the drain. What we're saying is now we are saying that in the non-ideal device, there's actually a capacitance here, and there's actually a capacitance here. Okay, so sorry, the capacitance, there's actually a capacitance here from the gate to source, and there's a capacitance from here to the bulk. But usually in general case, the bulk is tied to ground. So it's actually a capacitance to ground and a capacitance to ground here. So there is actually some stray capacitance sitting here, some parasitic capacitance arising from the junction, the depletion junction here, and from the gate to source, gate to drain. Okay, that is module 3. I'm all about telling you the effect of that module 3, more or less what is its approximate value and all that. But roughly when we do later on logical effort, we're going to take that the capacitance here and the capacitance here is roughly going to be the same as the gate capacitance roughly Okay, it may change with the future technology. That one you can check with the fab, but this is just for you to understand where it comes from. Okay, Ken?
Yeah, doctor.
Okay, great. I just need to make sure you get that. And now we're going to talk about subthreshold slope. Okay. All right. Since we are on the topic, right? Now we remove this charge layer because I'm going to take away the voltage on the gate. Okay, remove this charge layer. I'm going to ask you to stare at this again. This is NPN. NPN. What does that remind you of? NPN. What does that remind you of?
Transistor.
Specifically a bipolar junction transistor, right? Which is basically like you're joining two diodes in opposite direction. Okay, this is a transistor, but this is a field effect transistor. Why? Because you are having an electric field giving it an effect so that you can form a conductive path. That's why it's called a FET, field effect transistor. MOSFET, metal oxide semiconductor. This is metal. There's an oxide layer here and there's semiconductor here. Metal oxide semiconductor, field effect transistor, MOSFET. Okay. But within this MOSFET, there is a parasitic BJT. This, and this. It really is a BJT, right? But it's just that when you are actually putting a gate voltage here, the electrons go up to all the way here. The MOSFET effect is much more powerful than the BJT effect. But why are we studying this? We are studying this BJT because there is a situation where I might have a very small voltage here. Okay, this VG now I'm going to tell you is a very, very, very small voltage. And to emphasize how small it is, I'm going to make it a very small letter. Okay, it's a very small voltage. Why? Because it's supposed to be 0 volt, but you know when you talk about 0 volt in digital circuit, it's never really 0 volt, right? It's like 0, 0 0.1, 0 0.5, 0.1, 0 0.05, 0 0.12, because you know digital line is noisy, right? You agree with me?
Yes.
Okay, so when you have a 0 volt here, there is no conducting channel. Your MOSFET is turned off. It's not conducting. Okay, but there is a non-zero voltage here on the, okay, BJT is a collector emitter base. On the base terminal, there is a non-zero voltage. And guess what? When there's a non-zero voltage on the base terminal of BJT, got current flowing through here, right? That's how we use to estimate the leakage current of a MOSFET. So even though your MOSFET is supposed to be not conducting, there's no channel here, there's actually a very, very small amount of current that's flowing here. And if you're trying to save battery life, okay, you've got let's say my mobile phone has like 6 million transistors. All of them are leaking 1 femtoamps per hour. Okay. 1 femtoamps times 1 million transistor is femto is 10 to the 15, million is 10 to the 6. So it's about 10 to the 9. It's already a nanoamp, you know. So a nanoamp per hour, you can calculate how many hours, how much your battery life is leaking. So even though it's a very small amount, it adds up, and when it adds up a lot. That's why we need to take care about what we call this subthreshold behavior, right? Because that subthreshold behavior is basically it comes from the fact that there is a parasitic BJT here, and that although I'm not exactly having a terminal on the base, but what I essentially have is I have some kind of capacitive bias circuit lah. There's this circuit here, and then there is actually a capacitive coupling. This voltage is capacitively coupled to the base here of this NPN transistor, and therefore when it's coupled to the base, any slight change in VG, non-zero, right? It's not close to VTH, it's much smaller than VTH even, because you don't have a conducting channel here. It is actually inducing leakage current here, and we use the NPN bipolar transistor to sort of estimate how much is the leakage current of the MOSFET. Okay, so that is the question that you are trying to address here. By what factor would a subthreshold leakage current increase at room temperature at VGS equals 0? Assume N equals 1.4. Okay, so now I'm just going to take you back to the leakage current part. Okay, here, subthreshold conduction. Okay, if you, okay. Okay, if you were to stare at this equation here lah, and then you go for the BJT. This is the BJT collector current equation, and this is called the saturation current. You look at this term here, base to emitter voltage over the thermal voltage lah, VT. This is KT over Q lah, QKT. This is a constant lah. Okay, you look at this term. This is the bipolar junction transistor term. You stare at this, it looks the same. The only difference is there's a factor of N here. Where does the factor of N come from? The factor of N actually comes from, if you stare at it, it actually comes from the capacitive coupling of the capacitive coupling of the gate to the base lah. Okay, so the only difference is you have a factor of N there. Okay, and this is basically the equation for BJT lah. So this is how you're actually calculating the leakage current. This one is actually that effect of what they call that's the effect of the drain source current. What happens when you have a voltage across here, you can actually slightly change the resistance property of this BJT lah. So that's why you actually have this effect here lah. But I want you to focus on this part here. This part is where that thing will change lah. So you notice that this the current here is actually dependent on at some point there's a VTH here lah, VTO here. Okay, so if you change the VTO, by what factor will the leakage current change lah? Again, the way you read this is you don't memorize this. You try to understand where is this equation coming from, and you try to understand what are the factors. Each of these is actually a factor that will change the leakage current. Okay, can, huh? And you represent that by this lah. This is called the slump threshold slope. Basically, it's the slope of the leakage current over VGS lah. VGS, as I mentioned, is this voltage here, right? Because this voltage is slightly turning on your bipolar junction transistor. Did that help, Eugene?
Yeah.
Yes, okay. So it's actually looking at this equation. You're just applying. See, you see at the end of the day, all these fancy terms, they collapse it all up here, right? This is again the bipolar junction transistor, right? And then this is VTH, the threshold voltage. Yeah, this is the threshold voltage here, right? Because everything else, if you look at this, this is actually 10 to the power of VGS times 10 to the power of eta VDS minus V times 10 to the power. So you can actually break up this exponential term into 3 different multiplication term lah. Okay, and those 3 different terms, they lump it up into ID0 here lah, some constant lah. So the only thing that changes is only the one that is sensitive to V threshold lah. Okay, and the big picture here we're trying to get at lah. They throw all the equations, throw all the explanation to you, because trying to give you an understanding of the basic physics behind all of this. But at the end of the day, the simple point is this: current, these are all the levers to change it, and VTH, the device is somewhat sensitive to the threshold voltage in order to get the current, right? You change the threshold voltage a little bit, the current will change by quite a lot. And also the leakage current, not just the current, the leakage current is also sensitive to the threshold voltage, because later on in module 4, module 5, you will see that VTH is one of these transistor parameters that can change quite a lot during production. During the fabrication, that there's quite a lot of variation on VTH. And then I'm asking to quantify all of this, because you're going to say that, okay, VTH varies by 10% or by 20%. How much does the current vary, right? If this is 10-20%, right? Because if you know this 10-20%, how much the current vary, that's the percent change in drive current. So this is the variation in speed that you will expect in your chip. And if VTH changed by, again, 10-20%, how much does the sub-threshold leakage change? This is the variation in leakage power that your chip will draw. And where is the application? The application is, I have this kind of fabrication variation. That means although I design my chip to be like this, I can get certain multiples of variation in speed and certain multiples of variation in leakage current, leakage power, because leakage current is directly proportional to leakage power. Okay, this is where we're going. And you will see once you do the mathematics that the small changes in sub-threshold voltage will give you like 2 times, 3 times, 5 times, 600% change in leakage current. But it will give you a few tenths of percent or a few percent change in actual current. So the sensitivity of VTH will change your speed sort of linearly, sublinearly around there, but it will change your leakage current, the power that you are losing over time, which is the most important parameter for those kind of like embedded devices. It will change that by many multiples, factor of 2, factor of 3, factor of 4, big change. That's why process variation is the enemy of all these kind of low power devices. You got it? Okay, that's just to give you a motivation. Why am I making you do all this calculation lah? Yeah, it's very theoretical and all that, but there is a reason, because I want you to learn how to compute the multiple of subthreshold leakage as a function of the factors. And here, yeah, you may see all these numbers, but the key points to drive home to you, subthreshold leakage is dependent on temperature. Okay, if you change the temperature by 10 degrees, by 20 degrees, by 30 degrees, which you can do, right? Because it's a very small chip, very small area. I have some current, it's going to heat up. Okay, or if I have some variation in my subthreshold, in my VTH, my threshold voltage, right? How much does my threshold leakage change? Because this is what's going to actually matter in the real world. This is how those numbers will change. Okay, Ken? Can follow, Eugene?
Yeah, doctor.
Yeah, it is a lot. I know it's like boom, hit you on the head because I don't know that there's probably a variation in background in semiconductor physics and transistors, but so I was quite hoping that this textbook could try to equalize things lah. There's a lot to read, but if you can master it, you will really understand MOSFETs at a very fundamental level and a very deep level. And if you do that, you can start reasoning a lot about the origin of all these issues lah. This one is 2.14 is more like a toy problem lah. It's just asking you if this is a non-inverting buffer, why is it a bad idea lah? Okay, for this thing lah. I think my hint to you is you just look at the speed lah in which this can actually move lah. Okay, if you can get the transfer characteristic, you can explain that lah. If you have difficulty still with this, then maybe you can skip this lah. It's not so essential lah. This one is more like it's a toy problem to get you understand what they call strong pull up and weak pull up lah. So usually MOSFET okay, let me explain it. Try to explain it a little bit. Let me look for a MOSFET. Okay lah, this is a MOSFET. If your voltage VGS is fixed, then this is called a strong pull-up. That means your MOSFET is on. But there is a case where your voltage VGS, as the circuit operates, the source voltage is going to change, So your VGS is sort of changing, and reducing, So okay, I'll give you the answer a bit hint a bit for 2.14. Here in the case you look here, VGS is here, Okay, so this is going to go to logic 1. So this is going to be transmitting, right? So you're going to pull this up. So this is going to go from logic 0 to logic 1. So when it's logic 0 here, this is logic 1. Okay, so VGS is very large, right? So there's a large, nice, happy channel here. So as this is actually going up to logic 1 because it is charging through this path here, the VGS is actually reducing and reducing and reducing, So as the VGS is reducing, the channel here is going to be less and less and less and less. So it's like you're trying to pull it up, but then at the same time, you're reducing the amount of current. So it's like it's going up very fast first, then after that, it's going to slow down. And then at some point, it gets very, 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 very slow before it goes to logic 1. So this is called weak pull-up. Why? Because your VGS is changing as you are changing the node. So this is not great as a gate because it's slow. Whereas if you look at it like this kind of gate here, VGS is here. If you turn this on, it's going to go to logic 0. So this node is changing. The voltage here is going to go down, but VGS is always fixed. It's consistent, is fixed throughout the operation of the gate, which means that the channel that is formed there, that conductive path is always, you always guaranteed that number of electrons. So the current is always available, is kind of like consistent and all that. So this is just that. It's just the point to actually highlight this to you when you are studying this. Okay, Eugene, Ken?
Yeah.
Okay, great. So at this point, maybe we can take other questions or doubts if people have. If not, maybe let me touch a little bit on the assignments and then we can call it a night. Okay. Any more questions?
Doctor.
Yes.
I want to ask regarding the assignment. I encountered some DRC failure, like there is 63 DRC failure. Will it affect the analysis in assignment 1 or assignment 2?
Sorry, Shengli, can you repeat that again? I missed out. Which one were you asking on?
For the assignments.
Okay.
Yeah, when I running the Q4, I encounter some DRC failure.
Oh, design rule check failure.
Yeah.
Okay. Okay, like this, I think some of your friends also, like Shufan also mentioned, you get DRC failure and all that lah. My suggestion basically is, as long as you have post-static timing analysis and you can extract the SPAF file, don't worry about DRC failure. Okay, and this is how I'm going to distinguish it because I got several goals why I want to ask you to do this assignment. One of the major goals is just to let you experience what it's like kind of kind of doing the place and route and going all the way to the end lah. And when you have design rule check failure, it means that certain things like really cannot fit lah. And I just be quite frank with you lah. I think a lot of you also, maybe it's the first time doing this, you get a little bit of shock lah. You're like, why it takes so long and all that. Yeah, it does take long. If you actually can get this done in a day, I think is reasonable lah. So at least you let yourself, you pat yourself on the back lah. This is not really a small chip. It's not a big one either, but it's not a small chip. It's a quite a big processor lah. Okay, so you managed to do the place and route. Okay, the design rule check means there are certain like it is trying to do the routing and all that, and then it couldn't really converge 100%, and there's some rules that you had to violate and all that lah. In a real chip design, like let's say you in your actual job, you have no choice. You have to go back and fix it and fix it and fix it until everything passed. And this is where most of your back-end designers, the layout engineers, they have a lot of headache lah. Because if the tool doesn't solve it, they have to go in and manually fix it lah. Right? I'm not going to make you do that because our goal is not to make an IC. To get you through the process, but more importantly, you get through it lah. So I would just say lah, you can ignore the DRC check lah, as long as you have your pre-static timing analysis, your post-static timing analysis, and your spec file, you have enough already. Because I just want you to do the analysis. The whole point of this is that you get some realism. It's not just I give you any kind of circuit, like the circuit has actually been synthesized. So you can see that this can be applied in any design in the future in your workplace. So don't worry about layout issues. I had a little guidance here now that if you want to use a 7 nanometer, don't worry about the magic, because we don't even need to do the layout and the geometry lah. It just needs to be synthesized, meaning that it's actually converted into standard cells. Okay, place and route, meaning that actually there's an algorithm that try to position the different standard cells all into a chip layout, and they actually try to connect everything with wires so that you can actually get a good estimate of the wires. Because my main goal is just for you to get a good estimate of wires and for you to identify the near critical path and the critical path in your design, so that you know that is the problematic. And then if you can actually look at the static timing analysis and look at more nodes, you can actually even do a distribution of all the timing for all your nodes. Like how far apart is your critical path from your near critical path, and how far apart your near critical path with the average number in your circuit. Okay, and because as you will see later in the, which you should actually be touching now, you will see in the lectures on variability and reliability. Nowadays, it's not just the critical path you have to worry about. You have to actually worry about the near critical path, the path that are not really critical, but because of process variation, they can actually end up being a critical path for when you make the circuit, when you fabricate the chip. Okay, so try not to worry too much about that. And yeah, if it took you, I know BJ just recently asked if it took him like 24 hours to finish and all that. If you actually get to the point, you have the spec file, you have the post place and route static timing analysis, the pre-place and route, and then the post-place and route, the synthesis file, the Verilog file, but using the standard cells of the library. This is good enough. You can begin your analysis already. In fact, I don't actually need all of you to run it on your laptops. If you want to work in a group, then you all just make sure that somebody has actually gotten it to this part, synthesize. You can just reuse that file. It's okay. It's okay. It's more of you understand the process. This is IC design. This is where all the things can break. And to be quite frank, a place and route algorithm is not guaranteed to converge. So the fact that you actually have a design that managed to be place and route and all that, sometimes it's a bit of a miracle, So I would say, I would caution you, the default is that if you start throwing a lot of constraint, sometimes your place and route may not actually converge into a design. So that's when you have to actually kind of help it a little bit, like change the constraints, like increase the area, that kind of thing. So I don't want you to go into workplace thinking that when you click the button, the place and route always will give you a solution. No, it may not. That's the very sad part of it. That's actually why it's the most difficult part of the back end, because again, you think about it, you can already count, right? You can already count in your current RISC processor. You can count how many standard cells you have, how many flip-flops you have, how many of the gates you have. Now you're trying to wire all of that together, you know, in 7 layers or 8 layers of metal. What makes you think that there will always be a solution? So now if you think about it, you're like, oh crap, it's so challenging. Yeah, it is. It is. This is why it's difficult. And this is why industrial grade tools help a lot lah, because the algorithms are a bit more powerful and they got heuristics and all that lah. But for the purpose of illustrating this, okay lah, open source is okay lah. You don't have to run these multiple days and all that. But typically, I mean, if you check with your colleagues or friends who are in the industry, you just check with them lah. You ask them, let's say I do place and route, how many days does it take me to route for the entire IC? You just check with them lah, and then you get a sense of how reasonable or unreasonable is your own experience with this moderate size IC processor lah. Okay, I hope that helps.
Yep.
Okay, so what you're feeling now is you're feeling the initial uncertainty from people who have never done this before. Then you're like, oh, am I doing the right path and all that kind of stuff. Don't worry, get through it, get those things and keep asking those questions. This is normal. Get used to the uncertainty. It's very, very normal. The key thing that you have to learn from this uncertainty is you make sure you find out. And it's good. I take note. I think many of you are already like talking among yourselves, discussing among yourselves. That's very good. That's the way to work, because it's just too much for any one person to know lah. So if you can work with the team and get good feedback from each other, this is even better lah. Just make sure you understand lah. I mean, like I said, is the value is for you anyway. I'm not too interested in going to figure out who has copied who and all that lah. I mean, if you really don't get it, you're not going to get the extended assignment done on time. It's as simple as that. But if you've experienced it, you understand, then you know it's going to be okay. Right? More questions, please. Okay, if there's nothing at this point in time, so my encouragement really would be for those who are still lagging behind modules 1, 2, and 3, please just give it a quick push by this weekend to finish it up lah, because this is not really the big part of the course lah. That's just the basic. You should get started on the problem lah. So the serializer for high-speed serial links, I'm actually thinking about just a simple parallel to serial encoder lah. It's just a bunch of multiplexers. You can quickly sketch a little design, then you can check with me whether it's okay lah. This option 3, this is pretty much for BJ lah. But if any of you are interested, okay. But if not, I'm just thinking one of these two. This one is more challenging. This one you actually don't need to. If you don't want to lah, you actually don't need to use the tools. You can actually design this by hand. It's also okay. Then you manually just identify lah which standard cell you want to use. It's also possible. You don't actually need to use the tools for this. Okay, for option 2. I think lah, as a matter of guidance for you, you should actually try to finish module 5 as best as possible by end of this month. So you got another about a week and a half to go. Try to finish module 5 by then. In terms of the lectures, because this I'm anticipating is not going to be that easy to understand. It's not going to be that straightforward to understand. It's going to build a lot on module 1, 2, and 3, your basic understanding of the circuits. So module 4 will take you some time to get all of it. So you probably might need to listen to it 2 or 3 times. Module 5 also might take you some time to understand, and I'm anticipating module 4 and module 5, you guys will bug me to questions lah, because these are actually the more challenging. The concepts are not very obvious lah. They're a little bit subtle, because logical effort especially, the challenging thing is for the first time in your life, you know, you used to, if you take digital electronics at the undergraduate level, I think most of the lecturers, if they're a little bit sloppy, they'll tell you that, oh, the number of stages equals the propagation delay. You got more number of stages, you got more propagation delay. And then suddenly you come across logical effort and someone actually tells you, no, actually sometimes you can have more number of stages and it can actually make your chip go faster. The reason is because unlike digital electronics where your gate size is fixed, the width is fixed, here in ASIC design, we can change the width of the gate. That makes all the difference. And so when you can start changing the width of the gate, there is an optimum number of stages that will lead to the fastest design. And likewise, an optimum number of stages that will lead to a very low energy design. Okay, so that intuition I need you to build from the logical effort, not about the calculation, but the intuition, because it's going to take you quite far, and then be able to estimate delay and energy. Okay, so try to touch these lectures by the end of June, then you'll be in good state. If you leak over into July, I'm quite afraid assignment 2 you're going to have problem. You're not going to be able to get to it on time lah. Okay, so July you still have another about 3 weeks thereabouts lah, and the rest here is it's just additional knowledge for you lah. Okay, so final call for questions. If not, then maybe I'll just end the class at this point. So BJ, I just take a chance here to respond to your question. Yeah, the instruction cache and the data cache, you don't have to synthesize them. Most of your friends also don't. In fact, actually the instruction cache and data cache, they are actually a form of static RAM, static random access memory. They are not actually synthesized by RTL. Usually there's a separate way or separate path. At some point, I wanted to integrate these to you guys' work, but I think it's a bit too much. That's why I didn't do it. Here, there's an open source tool that can actually set up random access memory for you. It's not DRAM. I checked. I think it's SRAM. So it's SRAM. So it will actually set up the transistors and all that kind of things for you, the whole thing. So the dream, of course, is for you to be able to combine these to set up the instruction and data cache using these, and then link it together with your RISC-V because this is already people have done quite a lot of work here to actually set up all the tools and being able for you to specify the RAM in terms of its rows, columns, and all that. But we are not going to go through this. This is just in case you are very free in the coming few months or the coming few years, you can go and revisit your assignments and give it a shot. Okay, but this is how I envision it to be done. It's just not enough time. And judging by your feedback this round, I think the course is a little bit too heavy already. So I probably won't impose it. But just stick to RISC-V. If you can do something on that, it's already very good already. Because this is a bit too heavy. It's a bit too mounting.
Dr. Ho, I want to now actually I don't synthesize this the first assignment. I haven't finished yet. Actually, I get some hints from one of the member here, Mr. Wong, I think. So my synthesis is still running.
Okay. Again, my hint here is if you have some friends who have finished the synthesis and the place and route actually is synthesis then followed by place and route. You must finish the place and route. If there's some friends that have done that already, my view is not essential for you to really finish that You can go and borrow, share a little bit. You'll be nice to each other, and then you just use that file. Because the analysis is the important part. It's after the place and route. How do you analyze? That's the key point I'm aiming at. But for Intel people, because your bosses expect you to know a lot of things, so I try to give you a bit more but I don't actually mean to be so sadistic So if all of you can just kind of work together, the whole class can work together, just get one place and route, it's good enough really. Okay, so you don't actually have to go and reinvent the wheel and spend days and days and to do it It's not actually meant to be that way, but it's like whoever is fastest, can kind of give tips and all that. But it's not really going to be giving you marks for the synthesis and place and route. To be quite frank, I'm just going to look at your analysis and is it correct or not? Have you identified the critical path? How's your analysis on that? Can you tell me about the variability, reliability, aging? I'm just going to look at that, right? And then can you extract? Let's say now you got a sector. Can you actually extract? Can you actually draw for me the critical path, the gates, right? Can you tell me that after synthesis, what are the standard cells used? What are the sizes of the standard cells used? These kind of things So you understand what's happening with the tool, because we are in an era where tools will do everything for you. And to be quite frank, if you cannot think and analyze deep, you're going to be no difference from the, the diploma holder or even the fresh grad that, just click a bunch of buttons. Oh, the chip is designed already. Like that, everybody also can design chip, but they just click a bunch of buttons and then the chip set itself. No, but that's not the case, right? The secret is actually in, after the tool generate all of this for you, how do you go in and understand what has been done? How do you know what is the gap between what the tool has achieved between what is practically possible? That is the key point. The analysis, that the way of thinking that I'd like you to kind of adopt. Because later on when you actually go down to logical effort and all that, you can actually start using that to as a tool to analyze different logical implementation. Like for all of you know, adders and XOR, sorry, like the adders. There's so many different ways. You can use XOR logic. You can use different type of gates, AOI, OAI gates. You can use NAND NOR. You can use AND or NOT. The different ways to actually implement the same logic. There could be certain logical implementations that intrinsically they are faster than others, or intrinsically they save more energy than others. You won't do this for the whole chip, but let's say you have a few outstanding, like really these are the critical part or near critical part that is like boom, all the way at one end, right? These are the ones that actually you might go in and hand tune a little bit. Normally what they used to do in those old days when they create microprocessor, they will just identify critical part. Critical part, actually, they will just design by hand to try to reduce, break it up so that they can actually speed up the microprocessor because you have your max delay and your mean delay constraint. Mean delay sets the race time, max delay sets the maximum clock frequency. Max delay is actually the logic path that has the longest propagation delay in all your circuits. That sets the maximum clock frequency. So if on the critical path, I can reduce the max delay, you can sell a chip with a higher clock frequency already. And if I keep doing this for critical path and the next near critical path, the next, and slowly, I can really bring my chip up to a higher frequency. That's the point of all of this, is that you can actually look at the critical path and you can go like, I know I need to fix this. What are my options? Something like that. And one of the more straightforward options is you just do logical effort sizing. You change the width and all that to speed it up. The next, of course, would be a bit more heavy lifting. You start changing the logic, then you just use logical effort again to see that. And then you can also answer the problem, not just for speed, you can also have the same problem. Which path is the path that's burning the most energy? And then you can optimize for that, reduce the width and all that to make sure that is slower, you trade off speed, but if it's not a critical path, of course you can make it smaller and let it burn less energy. And in this day and age, being able to do that, you will get big returns because everybody is all about energy efficiency today, right? Yeah. So all these tools are very powerful. Applying them can be very tedious, but they are very powerful tools that help you reason about what to fix in your circuit if you know how to apply and look for it.
Sir.
Yep.
I have some question in the VLSI assignment 1. Can you open it? In the Q3, based on our own literature review, argue and justify on the expected. So we know the process variation is like the manufacturing variation. So that might be that is related to the token in the manufacturing. So I don't think we are able to see it in our simulation. So I am not clear about this question. What should we do?
Okay, what should you do? Okay, all right, great, good question. Okay, so now let's say you already synthesize, you already place and route, you have the complete chip already let's say okay, and then you map it to the standard cell. So every single logic I'm not asking you to do it, but I'm just saying that you could do it. You could actually just pick up any logic path. You tell me how is it implemented in standard cell and all that Now, question 3 is a little bit of an open-ended question. I throw open to you. I said, this is your design. You're using all these standard cells. And then you've already gone through the process variation and all these things, the lecture and all that already. How robust is your design to process variation and aging. Where is the weakest link in your design? How to answer that question? Then you start asking lah. Oh, process variation. Really, I'm looking for the really smallest transistor, right? Minimum size transistors, a bit of a problem, right? Because I have the line edge roughness, I have the dopant variation, or maybe if I happen to be using a low threshold voltage one, right? Threshold voltage I know is also a very problematic one. Or maybe this particular, I find that NAND and NOR gate, because they don't have as much regularity or something like that lah. Or maybe it's the flip-flops. I read something about flip-flops. They are not so, foolproof, or aging tends to happen when there's a maximum current, right? So aging tends to be like electron migration, where the areas where there's more current, there's more hotspots. So can I look at my design and can I identify where the areas where maybe I have a bunch of large gates that are together? So it's open-ended in that sense, because I want to see how you can take your conceptual and theoretical knowledge and apply it to a practical design in front of you. Because at the end of the day, okay, you are going to be designing chips, and nobody is going to tell you how to actually make it more robust to process it. Yeah, you know all the theory, you've gone through all of it here already, but how you're actually going to apply it? So like give you some hints, like for aging, you'll be looking at regions where you are actually giving hotspot in current, right? Hotspot in current, you probably know is those that big transistor got bigger current. If I actually have a region, the chip where there's more big transistors in one region, then that part maybe got more aging potential. So you can just circle there and flag that, okay, this is hotspot. I know that aging is related to the negative bias temperature instability, right? So this is a certain hotspot, or that it so happened I need to actually use a lot of the unit size gates. So unit size gates are a little bit more susceptible to these, or like let's say you talk about voltage variation, you see like, okay, this one voltage variation is this, but again, or maybe you can look at the distribution of your mean delay, max delay. You can say, oh, okay, most of my delays are like 2 standard deviation, 1 standard deviation away from the critical path or the near critical path. So I only need to fix the critical path, I bring that down, then it's going to be less variable. Or like because I understand the near critical path, the PVT can affect these to make it worse. I actually have to consider these 20 nets. These 20 nets or these 30 nets are the most critical because they are near critical, and any PVT variation will throw them off or something like that. So I want to see how you apply practical aspect of this to identify where is the weak spot in the design that you've built. I don't actually ask you to fix it. It's more of analysis. Just kind of flag like, if you really it come to this point that this risk score make or break, they tell you that the process variation is unacceptable or the aging is unacceptable. Make or break, what are you going to fix about it, or where are you going to start looking for it? I'm not asking you to fix. I'm just asking you to kind of argue out lah. So see whether how well can you apply your theoretical and conceptual knowledge to a very practical real design. Is that clear?
Yeah, so actually you mean we have to find out what's the weak point and how can we make it better in just analysis. And
yes, argue it out from your specific example, pull out from your example, my design got this. I don't really want an argument like, oh, MBTI. No, don't repeat the textbook. Don't copy and paste the textbook. No point. It's more of thinking work, like my design got this, my design got that, right? Because you already got the place and route file already. You sort of have it already, right? Even if you actually got the layout file, you can also talk about the layout, right? You just stare at it and things like that. But it's an exercise for you to go through to really apply. How do you connect that in practice lah? And it's very open-ended. So don't really worry so much about, it has to be correct, it has to be justifiable, but I'm not asking you to implement the solution. But you can suggest to me lah, maybe I need to space this out a little bit, or like look at, set some constraints around it, but the way we think about things scientifically is, number one, you have to identify where the problem, what's the hypothesis, and what are the reasons for it, the kind of reasoning behind it. Then based on that, only you can suggest the fix. You cannot just simply whack a fix. It doesn't work that way. You have to identify what is the problem, the root cause, Why this would happen, argue it out, give some example, from your real example, this one, do some analysis, then only you can suggest these are the solutions. Okay, can lah.
Okay, clear.
Open-ended, there is no, I can say no right or wrong lah. I also don't even know what the answer is lah. But I'll be reading your answer lah, and I'll be analyzing correct or not this one, reasoning okay or not, got good proof or not. That is how we'll be grading lah, this kind of question. Okay.
So we don't need to specific on the expected process. We can talk any other things, right?
Anything.
The variation, yeah.
Yes, the guidance is best if you tell me the effects with the biggest effect related to your design. Then you move from there. The one that has the biggest impact for your specific design. Yeah. We should anticipate lah. And then like I said, from the reason I put literature is because maybe you have come up with some, you can find some literature that says, okay, 7 nanometer technology or 35 nanometer technology, this is the major cause of variability, it's line edge roughness or this lah, that lah, right? Maybe you find something, or maybe you have some kind of Intel report somewhere that tells this kind of technology, you know, something like that lah. Or you might actually want to suggest that, oh, you have a special type of gate that is actually very resistant to this, so then you can mention this, and then sometimes that gate maybe have some weaknesses, is maybe not so, maybe it's more power consuming, or it's slower, or what, you know, you can argue it out lah. Okay, does that help? I hope that helps.
Okay, yeah, clear.
And number 4 is basically I want to see lah, you understand lah what happens if variability or aging, how does that change the speed and energy lah. Specifically talking about the critical path and near critical path lah. Again, you can apply some of the analysis that I went through in these lectures here. Like you can trace lah how many transistors lah. If you assume certain number of sigma variation based on some reported data lah. So because the OSU 35 nanometer is quite a popular process lah. So I presume people would have talked about it lah. Okay, Eugene has asked me what will be more relevant to hardware track. Option 2, Eugene, is high-speed serial links. You start designing a 8-bit parallel to serial encoder. This you can actually do by hand. You don't actually need to do any of this by software. You can identify the near critical and critical path lah. So if you are not so sure, you get a bit stuck. Again, this goes for all those who are not Intel or not semiconductor related, you're not so familiar with the tools and you have no interest whatsoever in picking up the tools, you can design option 2 by hand. Mark's the same. Intel people also, if you run out of time, you can also do option 2 lah. It's up to you. But I just present option 1 as a challenge that's more related to your work lah. So option 2, you can actually do by hand. What I actually want you to do is after you've already designed the logic circuit for the parallel to serial encoder, I don't need you to design everything because high-speed serial is pretty complicated. You have your clock circuit and all that. I'm just specifically asking you to just design the parallel to serial encoder, the part where you have 8 bits coming in parallel, you're serializing that part only. Okay, that's just basically an array of multiplexers lah, or array of AND gates or NAND gates. You just design that part. Okay, you can just run that design quickly through me. Just take a picture and ask me lah. I know some of you have asked me about assignment 1, but too simple lah, assignment 1. So it's like, okay, I'm just going to grade it lah. If you're a bit worried, then you can revise your answer lah, or you can check with your friends and all that lah. Yeah, but if you're not quite sure about your design for option 2, you can just run it by me. I ask you to actually, because after you've done your design, I actually want you to go and scroll through the FinFET standard cell library and you identify lah which standard cell you are going to use. That's basically which logic gate lah from that family you're going to use. You can actually go through the index, the list of gates lah. There's a nice HTML file that can actually see that, and you can all do this. So option 2, you can do everything by hand actually. There's nothing in option 2 that you actually need to use a software tool lah. Okay, I hope that answers the question, Eugene.
Thanks, Doctor.
All right. Anything else from anyone? Okay, if there's none, 1st July, we're having a lecture from Mr. Chia Chiu Yin. He is the head of IC design in MIMOS. He'll be sharing, generally, he'll talk a little bit about what an architect, an IC architect at the top level needs to consider. And he'll give some more detailed examples from his experience designing a permanent magnet synchronous motor IC controller lah. So it's an ASIC, and then they actually applied it to drive washing machine tub lah. And then I think he also talked a bit about the skill sets needed in IC design industry lah. So it's on the 1st of July, 8:30 to about 10 like that. Like it's going to talk only about 1.5 hours, but he's anticipating about half an hour of questions from you guys lah. So I also record the session if you cannot make it, but if you can make it, of course, it'd be kind of nice to engage with him lah. Someone who has done IC design for many years lah. He got his degree, I think, from Santa Clara University lah. And aside from that, maybe I'll just take another quick poll if we're going to have another discussion session in the next 1-2 weeks or so lah. Again, just to try to keep the momentum going lah. You guys are already starting the assignment, that's good, but you really need to be catching up to like aging and variability around this week, and then hopefully by end of June, early July, by end of June better lah, you start on the logical effort. Then you'll be in good time, you won't be too far behind, you'll be just nice. But if you are slipping up a little bit, then I'm afraid you'll be a bit far behind, so a bit difficult to catch up now. Okay, all right. Okay, last call. Any more questions? Okay, if no more questions, then good night, everyone. Have a good night. And if anything, as usual, you can WhatsApp me lah. It'll be a bit better. I prefer if you can actually WhatsApp in the main VLSI group lah. Then everybody has the benefit of getting the responses lah. I've tried to actually just copy and paste your questions lah, and answers there lah. Okay, all right. So in that case, good night, everybody. Take care and stay safe.
Thank you.
Right. Okay. Bye.
Thank you, Doctor.